So today we're very pleased to have Wojciech Ozanski, who's now at Florida State University. A number of us remember when he was our colleague, and we're delighted to see him again. Today he's going to talk about instantaneous gap loss of Sobolev regularity of solutions to the 2D incompressible Euler equation. And it will be a broad.
Right. Thank you very much for the kind invitation. And well, it's a pleasure to speak at USC as always. And in fact, on this occasion, is particularly I'm particularly happy to speak about it because the talk is based, in fact, on is influenced by the work of Diego Córdoba and Martínez-Zoroa, who they go speaking at the same colloquium last year. And after that, I joined forces with them and we work on 2D Euler. So here is 2D Euler equations. And we are only going to look at the case of the whole plane. And in fact, we are going to look at the vorticity formulation. So if we define curl omega, then the equation for omega is the following: is just the transport equation, where U can be recovered using Biot-Savart law. So in fact, this is I think it's 2 over pi integral of x minus y orthogonal omega of y x minus y squared. So this is actually very nice integrable. There is no principal value. It's just 2D Euler. And we're going to call such relation the Biot-Savart law, and I will use these brackets to denote the velocity coming from this vorticity for each time. Okay, so let me mention a few results about 2D Euler. The most classical results go back to the work of Ganter and Lichtenstein. I think it's 30. And they proved local posedness in CK alpha. Right, so given initial data in CK alpha, that's divergence free, there exists some finite time until which the unique solution exists and is regular until the time. And then there were a series of developments improving this in a different function. So this is in CK alpha. Alpha between 0, 1, and k is bigger or equal than 1. But if one want to work in Sobolev spaces, which is in a sense it's kind of equivalent, right? So if one wants the velocity field to be in some Sobolev space, W2P, WSP, sorry, SP, then well, you must have that S is bigger than d over P plus 1. Right, and this is because all we need, if you remember, there is a classical proof of local well-posedness, where basically all that is relevant, the most relevant is that L infinity includes WSP. Right, so in fact, if you have this relation, then not only you have embedding into L infinity, but it is in fact into some Hilbert spaces. And then the local well-posedness proof in several spaces work, but the way it is developed historically is that first Ebin and Marsden considered the case both in the year 70, the case P equal 2, so Hilbert case, and that was the case of the compact domain. Then there was work by Bourguignon and Brezis in 74, where they covered the NEP, but still they work in a compact domain. Now considering the case of the whole space, right, this is so far it's for all dimensions. The main work is due to Kato in 72, who covered the case P equals 2, and well, now this is in RD. Then Kato and Pons in 88. That's the case of NEP and the whole space. So that's basically the major results. And only a few years ago, there were very interesting developments that are concerned with Sobolev space that is critical. So not strictly bigger equal than this threshold, but for example, if it's equal, you might wonder if you can still persist with the proof of local posedness, and you cannot. Right, so that's the famous work of Bourgain and Lee in 2014 and 15, and they proved the ill-posedness. Right, so this is usually referred to as strong ill-posedness, which we can write shorthand notation as IP, and so this is in CK spaces. So first, the 2014 is in H D halves plus 1, and in CK spaces. And there were a series of developments from that. There was work by Elgindi Masmoudi, who proved a similar result, and there was work by Hyunju Kwon, who considered, for example, modified Biot-Savart law that is a bit more regular, and until some exponent you can prove strongly posedness, and then sharply from the exponent onwards you can prove local posedness. But maybe I can mention a few more results. So the work by Elgindi and Inji-Jong in 2017, they considered 2D Euler strongly posedness, but they constructed such solutions that are in Udovich class. Right, so Udovich class is referring to the case of bounded vorticity. It was proved a long time ago by Udovich that if vorticity is in L infinity, and also if you can allow some forcing, that is L1 into L infinity, you can have global in time, well-posedness, and uniqueness. Right, so they construct the strongly posedness result in this space. By the way, what this means is that these results say that, okay, let's take any smooth velocity field that is compactly supported. Then for any such velocity field, you can perturb it in some way in this norm, right, in the critical norm, such that there still exists a unique local in time solution, but that leaves that space instantaneously. But it's unique. And so they did that, but also in the Udovich class, which is a stronger result. And then there is a work by Inji-Jong, who proved still a 2D case, Udovich class. But there's an interesting property of that, is that you lose, right? So you have W as P regularity, and you can construct it in a way that when you evolve in time, you're going to lose this regularity continuously with respect to P. Right, so this is continuously in time. Right, so initially you're going to be some stronger Sobolev space, and then you're going to keep losing it. So in this context, let me mention our main result, right? So this is theorem number 1, which is due to Córdoba, Luis, Martínez-Zoroa. They are both at ICMAT Madrid, and myself.
The loss of the regularity, is it in P or in S?
It's in P.
In P, not in S.
No, not in S.
It's the same.
S is the same.
So the number of derivatives doesn't change, it's just the integrability of the.
Yes. Right. Right, so this is result from last year, and the first of these results is about norm inflation. You see, in these strongly posedness results, we are only concerned with being in some space initially and then instantaneously losing it. So what we prove is something stronger, in a sense that If you allow yourself even lower exponent, right? So some, let's see, if you are in 2D, this is just h2, right? For d equals 2. So if you allow yourself initial data that is for h beta below the 2, then you can instantaneously lose not only this h beta, but also the whole gap of other Sobolev spaces. So that's this main first result, right? So you can fix any time and any number you like, sufficiently large. And let's take beta between 0 and 1. And let's also fix some beta prime, which is going to be smaller than this beta, but bigger than a number given by 2 minus beta times beta divided by 2 minus beta squared. Given such parameters, we claim that there exists some initial vorticity that is C0 infinity, smooth with compact support, that initially, so this engineered vorticity, excuse me, is going to be order 1 in H beta space. But the unique, but the unique solution, omega of t, is going to become large in the H beta prime space, right? So this is a lower exponent. This is going to be bigger than k for times that are away from 0, but the interval is not short. Yeah, so by the way, I should comment, these results are for velocity fields in the Sobolev space, right? So for example, if we have omega in H beta, then that means that the velocity field is in H beta plus 1, right? So here, what is really the main concern is this beta between 0 and 1, right? Because then you are you have vorticity going to L2 at 0 and H1, which is critical, right? Because H2 is critical for velocity field, so vorticity is critical at H1. And by the way, this number, right? So you can imagine, okay, we take this beta, which is less than critical value. Now, what happens when you take this beta to be converging to 1, right? And you see if it goes to 1, this whole thing also goes to 1. So the gap becomes smaller, right? So this goes to 1 when beta goes to 1. But also when you allow your beta even less, it also goes to 0, right? When beta goes to 0, this goes to 0. So if we start from very irregular initial data, then actually your gap loss is almost the entire interval, because we cannot hope for anything less than 0, because we have L2 conservation, right? The transport equation. So the L2 norm is going to be preserved for all times. All right. So, and let me state the second theorem, which is can be obtained by iterating this claim. So this is same authors, and now this is the gap loss. And so here we state that, well, okay, you can have any epsilon, and you can, well, you pick any of this beta between 0, 1. And so we say that there exists some initial data, omega 0 now only in H beta, such that initially in H beta, we have small value, but we lose, right? So if you have a unique solution omega of t, then this norm is going to be infinity for all times. Right, this is the unique solution, which we actually define the notion of the unique solution in some non-standard way, but it's not something weird. It's actually basically something like locally it's C1. But we have to prove there is a unique solution and that and it satisfies these properties, right? So it starts from H beta space, but then instantaneously you lose not only this space, but a gap loss of spaces, and you never come back. Space. So
What happened to the reversibility of the Euler equation?
sorry.
That you can go backward in time.
Yeah, nothing happened. Let's see if we didn't think about it, but if you would go negative in time, I suspect the same thing would happen. Yeah, that would be my, yeah, you probably also lose.
Like finite interval around 0 with some regularity, and then outside of that interval, it's gonna.
No, it's only at 0 that you're going to have this H beta, and then instantaneously you would lose it. Yeah.
Even backward in time.
I think so. I can't guarantee. I will need to, but I don't see a reason why not. Yeah. Let's see. Yeah, sure. Yeah. Yes.
What's the space that you live in after losing H beta regularity?
Right. So you are locally smooth, and L2, and everywhere below, right at this number. If you are below this, then you're going to survive in this space. In particular, I stay in L2, and you stay in L infinity if you are L infinity initially. But in our case, this is not Euler class, so we don't construct these to be bounded. They are actually so. In fact, if you want to go from the first theorem to the second theorem, it's the argument is quite straightforward. So the way to do it is to stack them next to each other. Right, so if you were to prove theorem 2, then, all right, so let's consider a sequence of times, like 2 to the j. And then you have, for j equals 1, you have a solution that is compactly supported. And for this fixed time, actually for this fixed time, in this non-inflation result, we actually have the support remains of the same size. Right, so this first result is about non-inflation. So for some time until capital T equals 2j, this guy is under control, and it's going to grow a little bit in H beta. So we're going to have sequence of beta j is converging to that limit, right? 2 minus beta, beta 2 minus beta squared, and it's going to have large H beta j norm. Right, so large H beta j norm on time interval 2 to the minus 1 to 2. And then if you want to have, we can add up next piece, which is going to have smaller support, and it's going to behave better and for longer time. And at this point, you just have to make sure that you separate them at the right distance between each other. Right, so now this one is going to have large lower Sobolev norm, still above this number, but now this is going to be 2 to the minus 2 time until 4. All right, and so the argument is of course more involved because we need to show into, these are separate solutions and they're going to be interactions between them. Right, the velocity field is a non-local operator, but you can hope that if you have the large enough distances, the interactions will be small. And it has to be done a bit carefully, right? And so then you add more and more. And so if you want to have bound of this norm below by an arbitrarily large number, all you look at the sufficiently far away piece, and then you see you are going to have that bound for larger and larger time intervals.
How fast the distance between the supports grow with j?
This is exponential. Wait, I think this is actually triple exponential. And the triple exponential is required. I think it's triple. It's required for uniqueness, right? Because we claim this is the unique solution. It's not just some weird, crazy solution, right? This is unique in a reasonable sense. So for uniqueness, we need actually more regular, more separation. Just for constructing and showing convergence, I think single exponential is sufficient. Yeah, so in fact, when we want to estimate whatever happens here at sufficiently, so suppose we want to have h beta prime to be bigger than k, we look what happens around this guy in one huge ball, right? Because possibly for large times, we lose control over these, right? They behave the way we want only on the smaller intervals, right? But if you look at them all together, and if you scale things geometrically so that they will sum up the right way, then you can hope to control this. As long as this happens far away from you, you can look at this only, right? So that's how you can deduce from normal inflation the gap loss. But really, the heart of the matter is in this normal inflation, that you can indeed inflate lower Sobolev norms. So yeah, so I want to maybe explain some details how to construct this. But maybe if there is some question about the whole scheme, I can pause for a second.
Where do you Euler?
Let's see. Where do we need Euler? Okay, well, that comes from the structure of the of this construction, that you can construct some pieces and you basically interact between the two using the Biot-Savart law.
So I didn't see the use of Biot-Savart.
Well, because we didn't do any of the calculations yet. Yeah, we just the deduction from here to here. It uses some of the Euler theory, right? It's a transport equation. So the way we actually prove uniqueness is by trajectories, and it's very nice for transport equations. So the magic of this formula is that there is orthogonal here. So if one takes one piece of initial vorticity to be only radial, right? Only have dependence in r, then the velocity coming from that vorticity going to be only angular. And that's how you can cook up some scheme where you can get some inflation of some norm if you put the oscillations in the right place. So I'm gonna write some more about this, but maybe there's some more question about the. Yeah. Okay. So here it is. Okay, so we're going to define the initial vorticity of the following way, in the following way. Let's call this x omega of x and times 0. Let's see. So this is going to be f of sum of radius, and we're going to scale by proper multiplier times lambda to appropriate power. 1 minus beta plus the same for some other piece, lambda 1 minus beta times cosine of cosine of n alpha and n2 minus beta. Okay, so at this point we have two parameters. We have lambda and we have n. And of course r and alpha are the polar coordinates. Right, so the way this looks like is the following. We have f. Let's see. This is going to be f. And this looks like a radial function. And we're going to have g, which is a bit farther away. This is g. And so g is multiplied by these oscillations in the angle. Right, so I'm just going to draw something silly, like just something like this, so we can remember the oscillations in alpha. Okay. And also there is except for this piece of the radial vorticity, there will be some other one outside. which actually plays completely no role in the argument. The only reason this guy is here is to make sure that the mean of f vanishes. Because, well, if you want to deduce the same claim for the velocity, then you need to have zero mean to go from velocity to velocity. But otherwise, this guy, you can forget about him. All right, so if this guy has only dependence on the radius, then the velocity coming from this, right? So it's going to be some velocity u coming from this f will be only radial. Sorry, only angular. So I can draw some kind of lines that indicate that when you look at the term u times now omega, what really is going to matter for this primary influence is the u alpha dot d alpha omega times radius, right? Let's see, I think it's 1 over r, but all of this is order 1. So it doesn't matter. There's nothing going on at the origin. All right, so we see, because if you take this initial data and now you take the second piece and you take this alpha derivative, you're going to have extra factor of n. So you have really good control over that. Right? So as long as you make sure that this guy has appropriate dependence in the radius, you can make this guy to increase oscillations. Right? So in fact, the way to see this is that let's call this omega radial at 0, and this is going to be omega oscillatory at 0. Right, so the idea is that if you start evolving, then first we can keep the structure of this omega. I mean, we start with some pieces, right? Some inner piece, outer piece, and the question is if it gets preserved for some short times, and the answer is yes, which we're gonna explain. But if you believe that, then you would hope that this is going to behave like, well, the same factor, right? N minus beta g. And if this is really indeed this f influencing the oscillatory part, you're going to have this falling E side cosine, right? So it's going to be times cosine of n alpha p times angular part of velocity coming from f. Let me put this here. So this is times cosine n alpha minus t u alpha f. But this is this f. So lambda r lambda 1 minus beta and 1 2, and that's it. Right, so you see, because it grows inside, now we have cosine of high oscillations in alpha, but also this guy depends on the radius, right? So if this would, if this velocity would happen to be just a rigid, just the rigid rotation, it would do nothing, right? Because you wouldn't change the oscillations, right? But if you have something like, right, so if the derivative with respect to the radius of this guy, right, if you have bound below on this, then you have a different picture completely, right? Because initially you start with oscillations that are, right? And now if you have some variation in the radius of this velocity, then the oscillations for the outer part, let's say here, they're going to increase much faster than the ones in the inner part, right? So those oscillations will become tilted, and you're going to grow gradient. When you grow gradient, you can increase the higher Sobolev norms. Yeah. So that's the idea, right? That if you have this, then gradient of omega ost grows in time. That's the idea of the whole proof. So, and to make this more rigorous, we have to be more careful, right? Because this picture only describes the scenario when only the inner part influences the outer part. But there is, of course, the outer part can interact with itself. The outer part can influence the inner part. So we have to somehow find the setting to make this claim precise. But otherwise, that's really the idea, to keep track of the solution. And this is really the essence of the method of pseudo solution, right? So, there is many work that relate some interesting result in the Euler equations or SQG with high oscillations in one way or another. And there's work by Susan, instabilities. There's work very recently by Vishik, proved very interesting results. And there's method of pseudo solutions. For example, Stan last week was speaking about pseudo solutions. Convex integration. Right. So convex integration has to do with the fact that you can perturb your Euler equation to have some right-hand side, divergence of some Reynolds stress, and you can make an iterative procedure where in each step you add oscillations that cancel out this forcing. Right. It has to be done very carefully. And at the end, what you end up, you can get convergence in the sum topology, and you can get some weak solutions of Euler with some wild behavior. Right? But these are weak solutions. So what we do is we look at oscillations for initial data, but we really keep track of the behavior of the unique strong solution. This is all C0 infinity initially. And this guess, the guess of the linear order behavior, it really comes from the nature of the nonlinear term in the Euler equation. Right? It's velocity advecting the flow of vorticity. So we cook it up in some way that we think it would increase the oscillations, but we have to work to put the estimates together. So I think this is a very interesting method and has some applications in other methods. So for example, Diego was speaking about this method, the first application of this method last year in the CAMS colloquium, where they used it for SQG equation. Right? In SQG, it's the same equation, except the Biot-Savart law is different. It's a more singular velocity. Right? So there's no 2 bias free in SQG. And it's a bit different. It has a bit different geometry, and they had to cook up different pseudo solution, and they only prove the ill-posedness or non-existence. They do not prove the gap loss. Right? And so what we do here in the Euler equation, we employ the 2 parameters, the n and the lambda, and the relation between them. We explore this relation between them to optimize the growth. Right? So the n gives us control over the influence of the outer parts with respect to the inner part, and lambda compresses time, that it happens faster, and it has smaller support.
Decide about the scaling lambda to the power 1 minus beta.
Oh, right. Yeah. So, yeah, you see, so we must have initial vorticity to be order 1 in H beta. So the point is that this has a kind of this kind of guess really, right? This has same H beta norm for all alpha, for all lambda, for all n's. That gives us room to play with them, right? So in fact, only the H beta dot norm remains constant. The H2 norm becomes smaller when you take this larger and larger. Yeah, so I want to give some more precise description of how to make this whole thing work. Unless there are questions to this. Okay, right. So, okay, let's prove it then. So, what is really the pseudo solution? It's not really this because, well, this only includes the inner part, and to make things work, we have to include some errors. So, first you're going to define omega t, the unique global solution. Right, so this is a with initial data omega of x0. Right, so this is a zero infinity function. It's bounded Ludovic class, so we have a unique solution for all times. And so there's no ambiguity what this means. And we're also going to define the pseudo solution, which is our guess, but it's a bit better guess. And we're going to know this by omega bar. So everything with bars is pseudo, right? It's guess. And we will define this using, okay, so let's guess that the radial part remains the same. So it's going to be f of lambda r lambda to 1 minus beta. And the oscillatory part is going to be also quite the same, but the expression under the cosine is going to be more careful. So it's going to be n alpha minus integral 0 to t of u alpha of a omega. Okay, so I need to explain what is a. Operator a. A is simply the average in the angular variable. So this is average in alpha. Omega is our solution, the actual solution, right? So we define our guess using the actual solution. That's new. It doesn't happen in SQG, for example, so far. And then let's see. So this is the angular velocity coming from this. And the reason for this is that let's see. So if you take some omega and you average this in alpha, then this guy only depends on the radius, right? So when it only depends on the radius, it has the velocity coming from this vorticity has no radial component. That's why we can actually replace this u with u, use the same as u alpha. Okay, and in fact, we can write that a omega is going to be the radial part of the pseudo solution, which is this, right? That's the radial part, omega bar rad. And this other part we're going to call omega bar ost. And so we have plus a of omega ost plus the error, right? We had omega rad error. So this is defined by taking the difference, right? Omega rad minus pseudo solution. It's just a simple identity. And by the way, at this point, we only use the fact that A acting on omega rad bar is the same as omega rad bar, because the radial part by definition doesn't depend on the angle. Okay, so that's our guess, and you see it's different from that naive guess simply by adding this error. This is the error. So we have to be able to estimate it in some way. Okay, so there are 3 steps to do to prove the result. Let's see. Okay, I guess I can remove this. There are 3 steps. Let's see. So the first step, you have to show that the 2 bits, the radial part of the vorticity and the oscillatory part, remain radial and oscillatory, right? So let's say sup. I just call it that omega rad and omega ost remain localized. That basically, for the time we are considering, which is fixed, capital T, the support of whatever going to evolve from this f is going to be just a bit bigger, twice as big, let's say. That's the claim. I don't want to be too precise here. But also that we can already estimate the error of vorticity, that is the radial error. Right, so the way that the outer part is going to influence the inner part is actually very easy. And there is a very nice trick to show this. So in fact, you can bound this exponentially in n. That's the first step. Second step, we have to make sure that, right, so now the oscillatory part is not going to influence f too much. But now you have to make sure that the oscillatory part will not influence itself too much. And for this, we need that the velocity can be estimated. And to estimate the velocity, we need to estimate the vorticity in C1. Well, why in C1? I'm gonna show why this is important. So and you can bound this by, there are some numbers depending on the parameters, but they are kind of natural. But you have exponential growth in lambda. And this is for times that are between 0 and capital T. That's the second piece. And the third piece is that, right, so we have already estimated the L2 norm. Whenever there is no norm, this is L2. So we can estimate the radial error. Now all we need to estimate is the oscillatory error. And this one, we don't have that well under control, but we have some control. So in fact, this is going to be at most the L2 norm times lambda to some small power, delta over 2. Okay, so what is delta? Let's see. What is delta? Delta has to do with the relation between lambda and n. Right, so we have fixed capital T. And so we are also given beta prime, right? So beta prime was the loss of regularity in Sobolev spaces, and this was supposed to be bigger than 2 minus beta times beta over 2 minus beta squared. So anyway, if you have that beta prime fixed, then you can pick a small delta that you can add delta here and here that is still going to be bigger than that. Right, so given that, we fix delta such that this is a technical point, but we have to make this choice at some point, right? So b delta is going to be, let's see, so 2 plus delta minus beta times beta, 2 plus delta minus beta squared. And the point is this is still, well, it's bigger than that number, but it's strictly less than beta prime. Okay, and now we can relate lambda and n. And we make it that n to the power beta is the same as lambda to 2 minus 2 beta plus delta. This relation will become clear soon, but that's it. That's it. It's going to stay fixed. Right, so it's polynomial dependence. Okay, now once we have these 3 steps, we are done with the proof, because you can let's see. So now we can prove the main theorem, right, of the norm inflation. So let's see, what do we need? So we need that the omega for some in h beta prime is bigger or equal than something. We have to find one from below. So we have some choices how to do it. Right, what do we have? Well, we have all the it's a transport equation, so all the LP norms are preserved. L2 is preserved, and you can interpolate between some Sobolev spaces and L2. Right, so you can make a guess what to do. Right, this is a HS. Right, so suppose you start from 0, which is L2. Right, now you have H1, which is right. This is H1, and you have 2, which is H2, and so beta is somewhere here, and beta prime is somewhere here, right? So again, the claim of the theorem is that you can start initially having h beta norm order 1, and after, for some time interval, you can have this norm strictly bigger than whatever constant. So what can you do to get a lower bound on this? Well, how about we interpolate this guy between these two? Right, but I mean, you could do it, right? But it's useless because you only get upper bound on beta prime. Okay, so it doesn't work. How about you interpolate, let's see, beta between beta prime and 1? Can you do it? Well, maybe you can, but this is actually pretty hard because then you need to have, right? So if you're going to do this, then you must have lower bound on H beta. But that's very hard to prove. I mean, maybe you can do it, but we couldn't do it. Okay, so this doesn't work. So what else can you do? Well, so in any case, beta prime, which we want, must be on the endpoint of this interpolation, right, to get lower bound. So how about you take 1, interpolate 1 between beta prime and 2? Can you do it? Well, maybe you can, but here you go a bit too far. We don't have control of the solution to control second derivatives. We can only, you see, we have this error in the solution, which is doesn't look that easy, and we have some control over that thanks to step 2, but it's only in C1. C2, it's a bit hopeless. So this is too much. So the only way you can do it, in fact, to control beta prime from below, which I mean, the only way we are able to do is to go to negative space. So here we have minus eta. Now interpolate L2 between some negative Sobolev space and H beta prime. And that is easy because when you have L2 is our best friend, right? We have L2 conservation of both the actual solution and the pseudo solution. So they are going to bound from below for all times. And then we have lower bound on H beta if you can control some negative Sobolev norm from above. But above is better. It's easier, right? So all you do to prove the actual theorem is you interpolate. So what we say is that, right? So we take the L2 norm to the solution, and we interpolate between, let's see, so between some negative H minus eta, but it must be dotted, and with dotted H beta prime. In fact, you can do it for any Sobolev space HS, and S is anything between 0 and 1. And because this interpolation, you're going to have some powers here, but let's not bother ourselves. Some powers, who cares? Okay. So now what we prove is that this guy is bounded from above by the L2 norm times appropriate power of n and lambda. So this is actually 2 minus beta to the power minus eta. And the L2 norm, right? So then you take this guy on the left, and you have lower bound on HS. And this guy is in fact equal to G, which is coming from our pseudo solution, divided by 2 lambda n to the power beta. These powers don't matter that much, but it gives you the right growth of the HS norms. Right, so from this, so from all this thing, you get that you take the oscillatory part of the pseudo solution, it's going to be at least G in L2, and you're going to have the right power of the let's see, so it's going to be, and so this is in HS, some power of n to the power s divided by lambda power beta n to beta, and lambda to 2 minus beta times s. Okay, so And then all that remains to be done is to compare the pseudo solution between the actual solution and then right. So let's see, to compare this one with right, the bar with no bar, you have to play a bit more with interpolation. So in fact, we can also show that we have actually equivalence between these two quantities, and you can pick some exponent that is strictly bigger than beta, less than beta delta, and then interpolate between L2 and higher norms, and use this error you have for oscillatory part and the radial part. And then you get the claim. So how much time do I have? Roughly out of time.
We have another 5 minutes.
Okay. So if I can use 5 minutes, I can maybe just list the tools, the new tools that we use to prove these 3 steps. Okay, so oh yes, let's see. Let me remove the equations. Okay, so the first tool is that right. So if you take any velocity field coming only from the oscillatory part of the actual solution, then you can estimate it very nice, exponentially. This is very nice, and this is only in the support of the radial part. Yeah. Oh, by the way, so I didn't mention where we use step 2. So let me just go back here for a second, right? So to compare the solution with the actual solution, we use these 2 parts, first and third, and to get this lower bound on the negative Sobolev norm, so the upper bound on this one, right? The upper bound on the negative Sobolev norm. Here we use the fact that we have this control in C1, which can be used here, right? So we can control this error, and we can estimate this actually pointwise. Or you can write how is it? It's Zygmunt operator to power minus eta acting on omega ost bar. We have the formula, and then all you can do, you can write the Biot-Savart law in the polar coordinates, and you can divide the alpha integral into little pieces on which you have very good control, and then use the C1 bound. So, well, it's a bit technical, but the tools are very clean. So this is the first tool, and this is the second main tool. Second main tool is kind of well known. It's a log Lipschitz bound. Right. So whenever you have omega supported in the ball of radius constant over lambda, without ball of radius some other constant over lambda, and omega being of the form g of r and cosine of n alpha, and this holds. And in fact, this estimate goes back to the work of Udovich, right? So what this is saying is that if you have such omega, what you can do, you can estimate the Lipschitz norm. So let's see. So if we have UR, the radial part of the velocity, this is U of such omega minus UR of this omega at 2 different points. So this is Y, this is X. Then one can bound this by, let's see, this L infinity norm of omega, X minus Y, and log Lipschitz, we have extra log. So we have 1 plus log, and here it's 1 over lambda X minus Y. And so here is this goes back to Udovich. There's minor modification to do to get only the radial component, but that's easy. And now to get to this claim, only have to notice that, well, this omega initially it's n-periodic. It has n periods over 2 pi. And this is the structure of the Euler equation that remains, that persists for all times. It can be proved. Otherwise, you have no uniqueness, right? You can shift by angle. So in fact, you can always pick next to any x, y, that is like 1 over n away, that you're going to have 0, this guy. Right? Because it's n-periodic, right? Period, right? So this is actually like 2 pi over n-periodic. That's the period in angle. That's for omega. So you can pick y to be 0, for this to be 0. Then you have the bound of exactly what you need. And this is missing infinity now. Right? So, for example, the way you can use this tool is to get this bound for L2. If you write the PDE for this rat error, you see there's going to be lots of transport-like terms that are going to just vanish. And all the ones that not vanish, you can use tool A, tool B, and you get nice L2 bound using Gronwall. Yeah, and so this tool for bounding the oscillations, the velocity coming from highly oscillatory parts of vorticity, is actually a quite cute trick. So this is done by the, and this is my last thing. So this is done by the Pauli-Wiener trick. So Pauli-Wiener theorem says that a function is analytic if and only if the Fourier coefficients decay exponentially to 0. Right. So in fact, let's see. So you can see it in this case very easily, because when you write the so for example, if you write the radial part of the velocity using Biot-Savart law of something that's oscillating, then you're going to get cosine of n alpha times the integral in the angle in the radius of the following: r plus h squared sine alpha prime g r plus h sine n alpha prime d h d alpha prime over let's see, over h squared plus 2r plus h squared 1 minus cosine alpha prime. Yeah. Okay, so this looks a bit annoying, but it's actually very nice, because all this is saying is that you're looking for the n Fourier mode, the n Fourier coefficient of this function, right? So this is like taking the integral over the period 2 pi of this function, and now this radia which appear here, well, if you have oscillatory part strictly away from the inner part, then all of this is safe, in fact. So you see what you're going to pick. You're going to pick the function f to be sine of x over c plus 1 minus cosine of x. And this function has poles here, 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 and here. And they're going to go to 0 with c, when c goes to 0. Right? So they're going to go to 0, but otherwise you're analytic in this region until you hit the poles. Right? And so now you see, if you integrate, if you make this, let me just, this last calculation, it's very, I know, it's kind of a nice argument, I think. So if you have a function like that, let's calculate this Fourier coefficient. Right? So we have f of z e to I n z. We can move the contour of integration, right, from here to here. And here we are periodic, so these guys vanish. So we can basically change z into z plus I gamma for some small gamma. And now you see we have I gamma times n. This is like e to minus n gamma times integral of Fourier coefficient. And that's the decay you're going to get. And so we have here integral in r, but these things are all away from each other, so it's going to work. So anyway, you can use this to prove this estimate. and sorry, not this estimate for exponential decay in n, and then you put this together and it all works. So sorry for going over a bit.